Hi folks, welcome to 10.1 where we're going to talk about parabolas. So before we start, we're going to talk about what it means to be a conic section. I think that word can be pretty scary, but basically what we're doing is finding slices of cones. Okay, so a conic section literally means slices of cones. Now, specifically, you can tell from these diagrams over here, we're looking at slices of two cones that are stacked on top of each other. Now, when we take the two cones and stack them, if we slice them so that we only go through one of the cones diagonally, we'll end up with an ellipse. If we take a cone and we slice it diagonally, but we happen to go through the bottom of the cone, that's when we get the parabola. And then, last but not least, if we happen to make a slice go through two cones, we're going to end up with a hyperbola. And so those are going to be the three main shapes that we study in the next few sections. Okay, so before we take a look at working with parabolas, we're going to talk about completing the square. This is a really important concept that is helpful for all things conic sections, and it doesn't really come up again in Calc 1, but definitely comes up again in Calc 2. All right, so let's take a look at this first one. So x squared plus 6x is part of a quadratic, and here's what we mean by completing the square. We don't just mean completing the square of the power, but we mean like visually completing a square. So let's imagine what x squared could look like if I drew it as a square. Well, one side, there would be four sides, and all four sides would be the same length, so I can label them as x and x. Now, what about that plus 6x? So this plus 6x over here, I could add it all to one side, so I could add like plus 6, and then the areas would be x squared and 6x, which is how I get x squared plus 6x. But when we're talking about completing the square, what we actually want to do is we want to keep our square, all right? And we want to keep this as close to a square as possible, which means I'm not going to add all 6 units on one side. I'm actually going to add half of them. So plus 3 here, and then plus 3 down here. And as you can see, the second shape I drew is almost a square, but that square needs to be completed. And here's what's missing, this little green square down here, okay? So how does that apply to our equation? Well, what that means is we can write x squared plus 6x like this. So x squared plus 6x is equal to x plus 3 squared. So that would be the equivalent of saying the whole shape, all right, that whole thing. But we want to take away the green square, or the area of the green square. So we're going to take away 3 squared. Now, what might be helpful is to think about where you get this purple number from. This purple number is 6 divided by 2, and 6 came from here. So 6 divided by 2 gives us 3, and that's what we have there. And then we take this number and we square it to get the thing we take away. All right, so again, x squared plus 6x is equivalent to x plus 3 squared minus 9. All right. So let's take a look at how we might use completing the square to solve a quadratic equation. And we're going to take a look at example 2. Now, example 2 happens to be factorable. So let's go ahead and factor it so we can kind of check our answers at the end, okay? So if I were to factor this, I would get x minus 10 and x minus 8 equals 0, because 10 times 8 gives me 80, and negative 10 minus 8 gives me negative 18. And then I could set both of them equal to 0, and I get x equals 10 and x equals 8 as my two answers, okay? So let's see if we can get the same answers using completing the square. So before I complete the square, what I'm going to do is move this 80 to the other side, because I only want it to look like x squared plus bx, so I only want to keep these two terms here. So when I do that, I get x squared minus 18x equals negative 80. All right, now let's think about how we can apply completing the square to the x squared minus 18x. So visually, x squared is going to be x times x. Now, I know we have a subtraction here, and I know we can't have negative area, but we're going to imagine negative area in the sense of this particular diagram. So instead of taking 18 away from one side, I'm going to subtract 9 from one side and subtract 9 from the other side. Now, in order to complete the square, that means that there's a green square that I need to take away to keep it as x squared minus 18x. So here's what this looks like algebraically. Instead of x squared minus 18x, I can write that as x minus 9 squared, okay? And then minus 9 squared, or negative 9 squared. And that's going to equal negative 80. Okay, so now let's simplify. X minus 9 squared equals, minus 81 equals negative 80. Okay, now let's add the 81, and I get 1. All right, so we get x minus 9 equals 1, or x equals 10. All right, that is one answer. And that matches with one of our answers from above. However, we have to find the other answer. So x minus 9 could equal the other square root of 1, which is negative 1. And now when I add 9 to both sides, I will get 8. And so here are my two answers using completing the square. All right, so let's move on now to what a parabola actually is, okay? So what we're going to talk about is a geometric way of defining a parabola, which is a little bit different than just saying y equals x squared. All right, so let's start with these diagrams here. We're going to start with this one on the left. So a parabola actually has a few important points that maybe we've never heard of before. There's a focus, okay? That's a point that is sort of inside the curve of the parabola. And there is a directrix, which is a line that is on the outside of the parabola. And a geometric way of thinking about how we generate this parabola, okay, so how we got this blue curve, is it turns out that every point on this blue curve is the same distance from the directrix as it is from the focus. So every point on the parabola is equidistant to the directrix and the focus. Now, there's one specific distance that is going to be really helpful in getting us to determine our parabola. And that is this distance right here that I'm going to draw in the purple. The distance between the vertex and the focus. That distance we're going to call P, but we're going to have an absolute value around it because distance is always going to be positive. Now it turns out that the distance from the vertex to the directrix on the other side is also the absolute value of p. So that value p helps us determine the shortest distance between the focus and the parabola, or the directrix and the parabola. And that's what we're going to use to help us write some equations. All right. So let's take a look at a standard upward facing parabola, okay? Now this parabola will have an equation that we're going to see below, okay? Now this equation is going to be x minus h squared, okay, equals 4p y minus k. So let's identify what all these different pieces are. Well, h and k are going to be coordinates of the vertex. So h comma k, we have h and k. Those are from the vertex. Remember, the p is the distance from the vertex to the focus. And since our parabola is facing up, what we can say is that the focus is going to have the same x-coordinate, but we're going to add p to the y-coordinate to get the the focus coordinate. Now, you'll notice that in this diagram, they don't draw the directrix like we had over here. So we're going to go ahead and draw that in ourselves. And so we've got this line, which is the directrix, and the equation of that directrix is going to be y equals k minus p. So it's going to be k minus p because it's below the parabola. Okay. Now let's take a look at a case where parabolas might face up and down, or rather side to side. So in a case where I have things facing side to side, the general equation changes, and it changes to this. Y minus k squared equals 4p x minus h. So the y minus k and the x minus h, those switch places. But some things don't change. The vertex is still h comma k, just like it was above. And we still have a focus, but this focus is now to the right of the vertex, which means we're going to add p to the x value, not to the y value. Now, same thing, they don't draw that directrix, so let's go ahead and draw in our own directrix. And the equation of this directrix is going to be x equals h minus p, because it's to the left of the vertex, okay? So let me zoom back out for a moment so you can see all the different equations on the actual graphs. And what I want to show you before we finish this video is that there is a nice little table here of all of the equations, but I find it really helpful if I layer the equations on right to the diagram so I can kind of think about what I'm doing as I'm doing it, okay? All right, so we're going to stop here. We're going to come on back to do a whole bunch of examples on how to use these formulas and how to graph. Okay, see you there.